I'll start second order differential equations. I started that towards the end of last week's lecture. We did an example. I told you where differential equations are used. What example did we do? That was a very good application of second order differential equations. Yeah, go ahead. Yeah, find the depth of a well without any measuring equipment, yeah? Without having no electronic gadget or any sort of ruler whatsoever. We found the depth of a well, didn't we, yeah? Yeah, by using a second order differential equation. Lots of applications. You've done some with Kristen when you did first order differential equation. One very good application is trying to work out, how long does it take for, if I brought a cup of tea here, how long will it take for that to reach room temperature, yeah? Okay? Newton's law of cooling. When religious texts say, the Earth is 10,000 years old, the reason why scientists can dispute that is definitely wrong, simply is because if you apply Newton's rule of cooling, okay, you'll find that it takes 350 million years for the Earth's core to cool from 2,000 degrees centigrade to 200 degrees centigrade. That's how they can tell. It can't be just, 10,000 years old or whatever. Let's say 6,000 years old. I'm not too sure, okay. That is definitely wrong because, they can predict by Newton's law of cooling, how long it takes just to go from 2,000 to 200 degrees C to 200 degrees C, 350 million years, for example. So that's another application you could, a very interesting application. I want to look at second order. I want to concentrate on second order differential equations. Second order, of course, apply to things like vibrations. You want to look at a vibration problem. Your car, you see, I always had a complaint. As soon as you enter the university, how many of you can drive? Some of you can drive. Well, you might find, as soon as you enter the university, if you drive in, or rather than going to the car park there, if you drive in, you'll find the first sleeping policeman comes too early. It causes so much traffic. Okay? And if you've got good shock absorbers, like Citroens and some of the other cars, then maybe, you can sort of go with that sleeping policeman quite quickly, otherwise you can't. So vibrational problems are, in cars and in aircraft, and just generally vibrational problems are important. So that's where your second order comes in. I want to look at homogeneous second order differential equations. What's a second order differential equation? What is a second order differential equation? Come on, yeah. Yeah, you've got a second derivative in there. Yeah, so you've got something like a, okay, d2y, yeah, dx squared plus b dy dx plus cy is equal to some function of x, yeah? You've got something like that, yeah? Where a is not 0. Where a is not 0, okay? Otherwise, you wouldn't have, if a was 0, you wouldn't have a second order, would you? You wouldn't have that derivative there, okay? So, where a is not 0, what we'll look at is homogeneous. What do you think homogeneous might mean? The prefix homo means the same type. So, what do you think homogeneous means? Those of you who linear algebra should know. When we talk about homogeneous equations, what are we talking about? They're definitely the same type. And what else? What were they equal to? Go on then, Patrick.
Were they equal to 0?
Yeah. We're going to look at this first. We're going to look at second order differential equation with equal to 0. And then we'll look at, maybe in the second hour, we'll look at non-homogeneous or inhomogeneous. Okay, first we're going to look at this type of differential equation where the fx is equal to 0. And this is called homogeneous. This is called a homogeneous, differential equation. Sometimes second order differential equation. Now, if you want to solve this differential equation, a d2y dx squared plus b dy dx plus cy is equal to 0. What does that mean? If I say solve, what are you trying to find? Yeah, you're trying to find y, aren't you? A function of x, aren't you? Y is some function of x. Can you find a y? Okay. Can you find y, some function of x, yx? All right. Now, which one would you try? What could you try? Which y do you want to find? What does it need to satisfy? Or I'll just say, all right, let me just say x squared. That's a function of x, isn't it? What's wrong with that answer? Which y do you want to find? We say we want to find y. Which y do you want to find? Any old y. Y is equal to 3. Would that do? Y is equal to 7. Y is equal to x squared plus 7. Which y am I looking for? Go on, Patrick.
Y that fixes that equation.
Yeah, exactly. The one which you differentiate twice, you put it in there. You differentiate once, put it in there, you leave it alone and put it in there, you add them all together, you must get 0, mustn't you? Yeah? That's the y you're looking for. So x squared doesn't look like it's going to work, yeah? May do, may not, we don't know. I can't say it's going to work or not, yeah? So, sorry, have you got a question? Have you got a question?
Yeah, could you solve it in a quadratic way?
Well, we'll have a look at that. Are we going to solve it in a quadratic way? Let's have a look at. Let's see if we can. Now, if you look at this? What have you? What could you try? Should we try x squared? Or are we going to waste our time? Shall I try y is x squared? See if that works. Sine x. What I want to try x squared such that I put y x squared in there. I differentiate x squared to get 2x. Put it in there, and I put 2 in there. So no, it doesn't look like it's going to work because A, we don't know what A, B, and C are, do we? We don't know what they are. Unless A was, a half and B was -1 or whatever, we might work, but we don't know what they are. So no point trying x squared, no point trying x cubed or anything like that. They'll come across the same problem as x squared. So what could we try? Sine it? Yeah, go on. What made you try e to the mx? I'm out of infinite number of functions you try, okay? You chose that particular one. That is the one I'm going to try as well. You're quite right. What made you choose that one?
When you differentiate it, you can't increase by m squared.
Yes, exactly. If you try y is equal to e to the mx, okay? If you differentiate, you get another e to the mx function, don't you? Yeah? You differentiate twice, you get another e to the mx function. You differentiate 3 times, you get e to the mx. So a good, out of all the infinite number of functions you have, okay, a good function to try is try y is equal to e to the mx, okay? So let's try that, see what we get. Let's see if we can get anywhere with it. We may not, we may fail. Try y is equal to e to the mx. Now we want we want that function which satisfies this. So what do we need to do? If we want this function to satisfy that, we put in, we get 0 at the end. What do we need to do? Yeah?
You need to find the y dx.
Yeah, we need to differentiate once and twice, don't we? Yeah? So dy dx, you differentiate that once, what do you get? This is what I told you to learn. If you differentiate this once, what do you get? Come on, you must know this. This must be at your fingertips. Let's have someone else. Go on then, Rob. Sorry? Yeah, bring down the m, okay? So it's m e to the mx, okay? You need the second derivative, look there, okay? So differentiate again. D squared y dx squared. If you differentiate this again, what do you get? Go, sorry. Yeah, another m, which is m times m, which is m squared, yeah? Another m comes, m squared e to the mx, okay? What do we do with this then? What should we do with this? Yeah, put it into there. So a d2y dx squared, so we get a m squared e to the x, yeah? A m squared e to the mx. There's the b plus b, okay? dy dx, which is m e to the mx, plus c, y, okay? The function we tried was e to the mx. Now all that's got to equal 0. We've got to choose that function so it's equal to 0. If it doesn't equal to 0, it's definitely not going to work, is it? It's equal to 5 or x squared or something else, or e to the 7x. It's not going to work. So how would you solve that? Yeah, go ahead. Yeah, e to the mx is common. E to the mx, e to the mx, e to the mx. We can take that out. So you can write this as e to the mx, a m squared plus bm plus c is equal to 0. So we're page 733 or 732. 732 is where I started. Okay. All right. So you got e to the mx, am squared plus bm is equal to c. What can we? If a times b is 0, what can we say about a and b? Yep. Well, one of them is equal to 0, isn't it? Yeah. One of them is definitely equal to 0. We know that. We know e to the mx is equal to 0, or a to the m squared plus bm plus c is equal to 0. We definitely know that, don't we? That's a pen gone. All right, there's something wrong on there. Something. This is someone else, but this is someone else. Not the same students answering. Anybody want to have a go? There's still something wrong on there. The last line, something wrong on the last line. Anybody else want to have a go? Go on, you tell us. Yeah, e to the mx can't equal 0. If you plot the graph of e to the mx graph, okay, if you plot it, what does it look like? It's plus, depends if it's plus or minus, doesn't it? Yeah. If it's plus, it's going that way. If it's minus, it's going that way, isn't it? Yeah. So they should cross over at 1. Okay. It's never going to equal 0. So e to the mx is never 0. So you're left with that. Can you solve that? Can we solve that? Yeah. Because what is it? It's a quadratic. We know we can solve all quadratics since we've got complex numbers now. We know we can solve this. Okay. So let's solve this. So what types? If you look at that, that's a quadratic equation. Now you can have for a quadratic equation. You can have, what can you have? So for example, if you had, that's what we end up with. How do we solve that quadratic equation? Yeah, put it into the formula. We don't know what A, B, and C. We can put it into the formula. Yeah, we can write M is equal to minus B plus or minus square root of B squared minus 4AC all over 2A. Now, you have 3 different types of solution. What are the 3 different types of solution you can have? To this equation, to this quadratic, you know, AM squared plus BM plus C is equal to 0. So, yeah, well, we're not with a positive negative. What we're saying is there could be real and different, couldn't there? Yeah, they could have different. You could have a solution is 1 and 2, couldn't you? Or minus 1 and minus 1. So minus 1 plus 1, couldn't it? Yeah. So you might have a solution y is equal to, you might have real and different. Real. So you have one solution which is real and different. Okay. Real and different. Let's call this M1 and M2. M1 and M2. What else could we have to that quadratic? What other solution could we possibly have? No, it's equal to 0. See, you couldn't have M as 0 because 0 is 0. C may not be 0, you see. So M as 0 is not going to work. It may work if C is 0. Yeah, it'll work.
Real and C.
Sorry? Real the same, yeah. Real and equal, yeah. Could be real and equal, yeah. Real and equal, yeah. Let's call this M1 is equal to M2. Let's just call this M, yeah? So you've got the same, like x minus 1 all squared, yeah? X minus 1 all squared or x minus 3 all squared, yeah? That's a quadratic. You get x equal to 3, 2 roots. And what's the third? What else could you have? So let's have someone else. You want to have a go?
Yeah, complex.
Complex, you could have complex, couldn't you, yeah? You may have, that might be a negative, mightn't it, okay? That bit may be negative, so you could have complex. So we could have complex roots, okay? M is equal to alpha plus or minus j beta. So you've got 2 solutions. Well, when I say 2 solutions, you've got, look at this. Let's take that solution there. So one thing you could try, okay, is y1x is equal to e to the m1x is going to work, isn't it? Yeah? Okay? E to the m1x is going to work, yeah? We know because m1 is a solution, isn't it? If you put m1, you're going to get 0. So m1 is definitely going to work. No doubt about it. Okay? Another one, y2x is e to the m2x is going to work, yeah? You put m2 in there, that's definitely going to work. What we do is, because they're what we call linearly independent, we combine them together. We say, there may be a number in front. There may be a number in front. You know, if you differentiate, if you've got a in front, as long as that is 0, so, and there may be b, so we say y is equal to a e to the m1x plus b e to the m2x. We know both of them are going to work. We know that, okay? E to the m1x, and you could multiply that by a non-zero constant, okay? It's going to work. You multiply that by non-zero constant, it's going to work, because that gives you 0, doesn't it? Okay, if you put that in, it's going to give you 0. So if you've got real and different, then that's going to be your solution. If it's real and equal, that one there, real and equal, then your solution is going to be y is equal to a plus bx e to the mx. Okay, if it's real and equal, you've got one root, okay? You have a e to the mx, which is going to work, okay? Then you multiply by a factor of x, because you've got 2 solutions. It's quadratic, okay? Linear independence. Do you want to go, Thomas?
Just so I'll be back in a minute.
Can you not just go and then not come back and... If you're not feeling well, just go.
No, I'll be fine now.
I don't like you to stay with the class.
I'll
Just stay seated there. What about... Oh, come on. What about complex? Well, this is more harder. Right, complex. I know there's a bit of hand waving, but I can't go around without linear algebra. I can't show you why they're linearly independent and so on. What about if complex? M is equal to, guess what it's going to be? Y is equal to e to the alpha x, a cos beta x plus b sine beta x. Now the question naturally that those, at least the first two seem, they seem plausible. Okay, where does the sine and cos come from? Yeah.
I think you want to be the complex number form, he does.
Something to do with the complex numbers, yep. Because e to the j theta, yeah? What's e to the j theta equal to? What's e to the j theta equal to? The one we did last week.
Cos theta.
Yeah, but you get cos theta, it's cos theta plus j sine theta. That's why you get the cos and sines, you see? Okay? So it's if you've got complex roots, okay, then that is your solution going to be. Now, if we go back to the differential equation, where is it? Let me show you the differential equation again. And we've done all this. This is the differential equation we're trying to solve. This one here. So there it is. Yeah. This is the one we're trying to solve. This one here. Can you think of Can you think of a solution? When I tell you, you're going to say, "Oh yeah, why didn't I think of that? I'm so silly." That's what you're going to say. I guarantee you when I tell you a solution to that. You want to find, sorry? Give me a solution to that. Give me a y where that's going to work. Y is equal to x squared is not going to work. We did that. Y is equal to x cubed is not going to work. Y is equal to 7 is not going to work. But there's a y which is going to definitely work. I'll give you a clue. It's called the trivial solution. What do you mean by normal one? That's vague, isn't it? Sorry? No. A bit of, what to the power one? Anyway, that doesn't. I'm not too sure what you mean by power one. When I tell you it's going to work, you say, "Oh yeah, what do I think?" I'll tell you, you will say that to yourself. Yep. Yeah, of course. 0. Try y is equal to 0. It's going to work, isn't it? You put y is equal to 0 in there. You put in the y, c times 0 is 0, differentiate 0, you get 0, differentiate twice, you get 0, you get 0 plus 0 plus 0, yeah? Okay, you're going to get 0 is equal to 0, which is correct, isn't it? Yeah? So when we're looking at this, okay, we look at non-trivial solutions. I made that mistake where I said, find the solution, and people have put down, students, because I've told them, they turn around and use that weapon against me, so, y is equal to 0 is the solution. They can't be able to solve they don't know how to solve the differential equation, they just want to y is equal to 0. And you get no marks for saying we're looking for a non-trivial solution. So if you've got the solution y is equal to 0, okay, that's called a trivial solution. But in this, we're looking at non-trivial solutions. We want to find, not the obvious one, y is equal to 0. Like I said, and there's no point doing all this work. There's no point trying y is equal to e to the mx. You're wasting your time. Okay, no, what's the point? There's the solution, there it is, straight away. Yeah? So we're interested in non-trivial solutions to this. So those are what we have. So depending on, perhaps I could give you the flow chart. I was going to show at the end, but this is what you have. In summary, this is what we have. If you've got, let me zoom into this. If you've got a second order differential equation there, okay. If you've got, this is your characteristic equation, your quadratic, okay. All you do is solve the quadratic. If it's real and different, m1, m2, you get this solution, y is equal to a e to the m1x plus b e to the m2x. If real and equal, then that's the solution. If it's complex, that's the solution, yeah? So all you end, this is why I'm saying this is easier, is all you're doing is solving quadratic equations. That's all you've got to do, just really end up solve quadratic, what's that page 737? So let's do some examples. Let's solve, who's the class rep? Right there, who are the class reps? One of you are, who else? Hannah, is there anybody else? What else from this group? Is anybody joined on the physics? Who's the class rep? Oh, she's not here, is she? Oh, yeah. What happened to the Skype thing? When you going to supposed to Skype this lecture? Sorry? Oh, well, I'll leave it now. I've got this video now. Anyway, it's working at the moment if it doesn't. Solve. Okay, let's solve this. I mean, the reason why I ask who the class rep is, it's pretty cold in this room, isn't it? Yeah. You pay, well, that's up to you. I feel cold, but I don't know about you. Solve d squared y dx squared, okay, plus 2 dy dx minus 3y is, okay, sorry, minus 3y is equal to 0. So what are we trying to find? When it says solve that. What does that mean then? Oh, it goes too far, doesn't it? Oh, come on. No, what's wrong with this? Why is it so sensitive? Okay, how do we solve? What is it? When I say solve, what are we trying to find? Remember, I said to you from really day one, you know, if you don't know what's required of you, not just on this module, any module you do, if you don't know what's required, if you get a piece of coursework and you don't know what's required of you, you can't do it. You need to know what's required of you. And in mathematics, it's slightly easier. You know, it might just say integrate this function. You know, I remember in the last test, you know, if you look at the last test you did for MT1, most students did not do well on that applications questions, the one about glazing a window, yeah? Glazing a window. Many people didn't do very well because, and I was talking to Rob about this and one of other students, they're saying, because you have to decode that language, you see? And you would expect maybe the physics and astronomy student might perform better on that question, but it didn't show, you know. Because in maths, you know, if it's a straight maths question, I think Rob said, you should have just said, find the maximum minimum, that's it, you know. I mean, you telling me that, you know, and you go, I prefer that than do you dress it up in this sort of applications orientation, which is fair enough, you know, but, anyway, what do we solve? Again, what are we trying to find? Yep. Y, yeah, we want to find y. Now, how do we find y? What do you need to solve? Yeah, quadratic equation. You don't have to treat it for each time. All you do is solve the equivalent quadratic equation. Now, what's the quadratic equation going to be in this case? What's it going to be?
Y equal to E of N, right?
Yeah, no, we don't want to do that each time. No, just you can do it directly now.
So if the M
Okay, let's solve this out, Henry.
The m squared
Yep.
is 2m minus 3.
Yeah, 2m minus 3 is equal to 0, yeah? Okay, that's why we get that quadratic, okay? That's minus 3. Now, how do you solve that quadratic? How do we solve this quadratic? I cannot believe that no one in this class knows how to... Go on there, Hannah. You tell me. Sorry? Yeah, factorize into what? 3 and minus 1. Yeah, okay. M plus 3, okay? M minus 1 is equal to 0. Does that work? It looks like it, doesn't it? Yeah? Looks like it's going to work. So M1 is equal to minus 3, and M2 is equal to 1, isn't it? Plus 1, yeah? So what type of solution have we got? What type of solution have we got?
Real and different.
Real and different, yeah? So you go to your summary chart or whatever, you go there and you say, okay, I've got real and different, yeah? Real and different, so my solution is going to be y is equal to ae to the m1x plus be to the m2x, yeah? Okay, it's real and different, that's what you got, real and different, m1, m2, so my solution is going to be y, so we can't write y, is equal to ae to the minus 3x plus be to the x, yeah? Okay, that's your solution for that differential equation. That's what it is to it, there's nothing else to say. It's called the general solution. It's called the general solution. Okay, this is general solution. All right, let's do another one. I think this is page 3, I think. Okay. Let's solve dx squared plus 2 dy dx plus y is equal to 0. It's again a homogeneous equation, isn't it? Yeah? Equal to 0, the same type. So how do we solve this one then? How do we solve this one? Go on, Rob.
M squared.
Yep. Your capture is going to m squared, yep.
Plus 2m.
Yeah, plus 2m
Plus 1 equals 0.
plus 1 equals 0. Can we factorize this? You'd better recognize this one. Sorry? Yeah, m plus 1 all squared, exactly. M plus 1 all squared is equal to 0. M is equal to what? Minus 1. So what type of solution have we got? Real and equal, isn't it? Real and the same. I think you said the same. Real and equal. Okay, real and equal. So there's real and equal. Okay. Zoom into that. So y is equal to a plus bx e to the mx, yeah? Okay, a plus bx e to the mx. In this case, m is minus 1. So we have y is equal to a plus bx e to the minus x, yeah? Okay, what about this one? Find the general solution. Find the general solution of d2y dx squared plus dy dx plus y is equal to 0. So how do we do this one? Let's have someone completely different to answer this question. Yep, what do we get? What's the characteristic equation then? Yep, m squared plus m plus 1 is equal to 0, isn't it? Yeah? Okay, that's what we get. The quadratic, okay, m squared plus m plus 1. How do we solve this one? Do we factorize? No. Well, they can all be, you're right, they can all be factorized, not an issue, but factorizing something, root 5 over 7 or something. We don't want those, you don't want to shop around or search for, what are the roots of this equation. You want simple roots, 1 and 2 or a half and minus 1. It's okay, you can do that, but here the roots are they can all be factorized, not that they can't, but the roots are not going to be that easy for this one anyway. So how are we going to solve this then? How are we going to solve this? Go ahead. Yeah, the quadratic formula, okay, which is m is minus b plus or minus b squared minus 4ac all over 2a. And what is abc in this case? Look at abc. What is it? What is it in this case? Yes, 1, isn't it? In each case. A is 1, b is 1, and c is 1, isn't it? Yeah? A is 1, b is 1, c is 1. So we get minus 1 plus or minus 1 squared minus 4, isn't it? 4 times 1 gives you 4, doesn't it? Yeah? All over 2 times 1, which gives you 2. So we get minus 1 plus or minus square root of what? Minus 3 all over 2. What's the problem with square root of minus 3? What's square root of minus 3? What is that equal to?
J3.
Yeah, j root 3, isn't it? J root 3, is it? Okay. So this is minus 1 plus or minus, that's minus, isn't it? Yeah. Plus or minus j root 3 all over 2, which we can also write as minus a half plus or minus j root 3 over 2. Yeah, that's my solutions. That's what my m is equal to, yeah? Okay, so what type of solution have we got this time? Complex, and we've got complex roots, okay? So then you go down to your formula, okay? Complex roots. And you find m is equal to alpha plus or minus j beta gives you y is equal to e to the alpha x, yeah? A cos beta x plus b sine beta x, yeah? Okay, what is alpha and beta in this case? In this case, what's alpha and what's beta? They would be put off by Greek letters. Yeah, alpha is minus half, isn't it? Yeah, alpha, that is alpha, isn't it? Yeah? And what are beta? Just root 3 over 2, yeah? Yeah, just root 3 over 2, yeah. And that is beta. Okay, so our solutions are y is equal to, it says e to the alpha x, isn't it? Yeah? Okay, if you look, oh, sorry, you can't see. Y, it says e to the alpha x, okay, it says e to the alpha x, a cos beta x plus b sine beta x, yeah? And in this case, alpha, of course, is minus a half, isn't it? Yeah? Alpha minus, so e to the minus a half x What's in square brackets? You tell me. What do I get inside the square brackets? Sorry, go ahead. Yeah, a cos, yep. Yeah, root 3 over 2x. Go ahead.
Plus B sine.
Yeah, plus b sine. Yeah, root 3 over 2x. That's your solution, isn't it? Yeah? That is your solution. Solve d2y dx squared plus 3 dy dx plus cos x is equal to 0. Solve that one. How do we solve this then? What's the characteristic equation? Why doesn't it work? You're right. It's a decoy question. You're quite right. I'm trying to trip you up. I'm setting a trap for you. You're quite right. It doesn't work. Why doesn't it work? Work for the previous 3 or 4 we done. Why suddenly it doesn't work for this one then? Not do the trig function. Not that so much. Well,
Does it have a Y or?
there's something to do with y. Yeah, something to do with y. I agree. Sorry. Something to do with that, yeah. But can you think of something? What do you think? How do you think I tripped you up? If I go back with this is what we had. This is what we were given. That was a differential equation. That one there. Okay, that's what I said it was a homogeneous differential equation. What about that one? Sorry, it hasn't got y. It doesn't have to have a y, but something else. Nothing to do with the cos x. You're right. So let's go behind you. Go ahead. That's true, yeah. So what? So what are you saying? That's true. Go on then.
Homogeneous is the same, but this one's got different.
Yeah, exactly. It's non-homogeneous. Yeah, cos x is got to go to the other side. I didn't give it to you in standard form, so be careful. This should have been written in standard form. This should be written like this: d2y dx squared plus 3 dy dx is equal to minus cos x. That's how I should have given it to you, but I didn't. Because I look out for that, okay? It's got to have a d2y dx squared plus b dy dx plus cy. Okay, that's what it is. It's got cy, you know. You haven't, you got, you know, c, okay, cy is 0. C is 0, clearly. Okay, but that's equal to 0, but you haven't got 0. It's actually equal to minus cos x. So it's what we call a non-homogeneous, we call it a non-homogeneous differential equation. So really, this is what you want to follow. These three, it's quite straightforward. Solve the quadratic, okay? I don't know what's wrong with this. Solve the quadratic. If you solve the quadratic, all you do is solve that quadratic, and depending on what type of solution you have, okay, I'm sure this is in the maths handbook, but check it out. I'm pretty sure it is. But you know, you need to check it out. Any questions on that?